if f of z is analytic in inside a circle C with center with center at say z0, then the symbol means for all. Okay, for all, this symbol means for all z inside C, this f of z can be expressed as f of z is equal to f of z0, the same like last semester 2 what we had, plus z minus z0 f dash of z0 by 1 factorial plus z minus z0 whole square by 2 factorial into f2 dash of z0 plus etc. Plus means series it is, so it will extend up to infinity. Okay, means infinite number of terms are there, and this point is, this series is convergent at every point inside C, means for when you calculate this one you are going to get a finite value in the series. Okay, and this type of expression we call that as a Taylor's series, means here f of z equal to f of z0 plus z minus z0 upon 1 factorial f dash z0 plus etc. plus z minus z0 the whole square by 2 factorial f2 dash z0 plus etc. Okay, so last year what you had was, instead of z you used to have x minus x0 upon 1 factorial f dash of x0, like that. Okay, here we are dealing with complex numbers, complex variables, so here you are having z and all. Okay, then now Laurent series means, so this can be again rewritten as, if we want to write, suppose I put z minus z0, that is not common to use. If I put z minus z0 equal to h, then here z is equal to z0 plus h. So this formula can be changed. So instead of f of z, you can write f of z0 plus h is equal to f of z0 plus h into f dash of z0, like that. Means you can change that formula. Okay, so that is not so common, so I am not writing that one. Now if you put z0 equal to 0, means if z0 equal to 0, if this point is 0, f of 0 plus z by 1 factorial f dash of 0 plus etc. Means I hope you remember this one, f of 0 plus a x by 1 factorial f dash of 0 plus x square by 2 factorial x square by 2 factorial plus so into f2 dash of 0 plus etc. Okay, this we used to call this as Maclaurin series. Maclaurin series, that is this you had. That same thing only here. If z0 equal to 0, if you put, you will get another series. This Maclaurin series we use to get the expansion of functions. Okay, sin x, you have expansion of sin x is x by 1 fact x minus, just a second, sin x is x minus x cube by 3 factorial plus x raised to 5 upon 5 factorial. Like this we used to have expansions and all using this Maclaurin series. So that same concept is here also, means Maclaurin series we can write from this Taylor's series. Okay, that I will give you expansion, I will give you that some formula. Then here Taylor series is important, that's why I am not going to give much stress here. Laurent series is very important here. So here, then second one, Lorentz series. Laurent series expansion. This is very important. Taylor series already you had that in terms of x, so you know how to find that one. Now Laurent series expansion, mainly we define this Laurent series for annular regions. Annular region means when you have like this. So suppose this is a curve, C1 and C2 are two closed curves, C1, C2. Closed curve here we will consider it as circle. So this is suppose radius is R2. Here center say Z0 and here the radius of bigger circle say R1. Okay, so R1 is radius of bigger circle and R2 is radius of smaller circle. So we define a function on such circles we call as means circle with same center and different radius. Circle with same center and different radii we call that as concentric circles. Concentric circles. So here we define an f of z which is analytic on C1, on C2, inside this one and in this annular region. Okay, in this annular region means the region between C1 and C2, annular region. So we define f of z is analytic on C1, on C2 and the annular region say R. This is annular region R means between the circles. Okay, then for any point z in this R means if you define any point z inside this R, inside this region, we can the statement if you write it will be if C1 and C2 are two concentric circles, you can note down this, are two concentric circles of radii R1 and R2 with center at Z0 and if f of z is analytic on C1 and C2, f of z is analytic on C1 and C2 and in the annular region are between these two circles, between the two circles, then for any point z, in this R, we can define f of z is equal to summation n equal to 0 to infinity a n z minus z0 raised to n plus summation n equal to 1 to infinity bn z minus z0 raised to minus n. Don't worry, you need not learn this form and all, you must just know this one. Okay, where here an bn again, an is given by 1 upon 2 pi I integral over C1 f of say omega, any term f of omega by means instead of z we use here omega upon omega minus z0 raised to n plus 1 d omega or dw as you like, and bn is given by 1 by 2 pi I integral over C2 f of omega divided by omega minus z0 raised to minus n plus 1 d omega. Okay, so This is the definition of Laurent series expansion. Okay, so this is Laurent series expansion. If you look at this one, you have to just check the function, means two circles will be there, concentric circles will be there, and then one with radius, small radius, and one with other radius, and the function f of z is analytic on C1, on C2, and between C1 and C2, means in the annular region R, and if z is any point in this region R, in this annular region, then you can define f of z as sum of these two series. If you look at this one, the first series here, see, raised to n, and here it is minus n. Okay, so this is a positive series. You are going to get z minus z0 raised to 1, z minus z0 raised to 2, like that positive terms you are getting, and here what you are going to get is something negative, means here z minus z0 raised to say minus 1, then minus 2, minus 3, like that, or you can say 1 upon z minus z0 raised to say 1, 2, 3, like that. Okay, so here one positive series you are getting, and here other negative powers you are getting, means positive powers, and here one negative powers. Okay, then now how to this what I have written as a n b n, you just note it down only. It is not necessary to learn this one, means this is of a bit higher level to understand, so don't go with that. Okay, and here now if you look at this one, this positive part means the part an, this is very important, that is this, the part summation n equal to 0 to infinity, this positive powers an into z minus z0 raised to n, this is, so this consists of positive powers of z minus, say z minus z0, or if z0 equal to say a, you can write as z minus a the whole raised to n. So I am keeping it as z0 only raised to n. Then this part is called as the analytic part. Okay, this positive part, that is called as the analytic part, or you can call that as the regular part. Okay, regular part. And the second part, that means the part, this summation n equal to 1 to infinity bn into z minus z0 raised to minus n, this part we call this as, means these are the negative powers of z minus z0. Okay, negative powers, this we call as the principal part. This is a principal part, or that is otherwise called, this is a principal part of the Lorentz series. Okay, so the positive part, that is the analytic part or the regular part of Lorentz series, and the negative part is called as the principal part of Lorentz series. Okay, so just go through this one. While doing the problems, we are not going to use any of these terms. Okay, now some results I will give you. Already you had this, so but still again just note it down. This result we are getting from Maclaurin series, that is e raised to z is equal to, all of you know how to solve this one. Okay, I hope you remember last semester we did f of z equal to e raised to z, then you will find f dash of z, f2 dash of z. Okay. Then you will find f dash of 0, then f2 dash of 0, and then we will substitute that in Maclaurin series term, means that formula will substitute, and you are getting this expansion what I am going to write. Okay, now you need to learn this expansions because we may be using it. So 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial plus etc., where condition here it is mod of z will be less than infinity, and that is that expansion of e raised to z. Then sin z, all of you may be knowing this one, direct secondary students, please note down this, z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus z raised to 7 upon 7 factorial, and so on. Okay, here also means everywhere mod of z will be less than 1, almost all mod of z less than infinity, not 1, sorry, mod of z is less than infinity, means it's a series, so mod of z is less than infinity. Then similarly cos of z is equal to 1 minus z square by 2 factorial, means even terms will come here, plus z raised to 4 by 4 factorial minus z raised to 6 by 6 factorial plus etc. Then we have sin h is a hyperbolic sine and cosine, so that also we may not be using too much. So now log of 1 plus x if we were having, so there we were having with x real terms. Okay, now with complex term log of 1 plus z is z minus z square by 2 plus z cube by 3. This all we are getting from that Maclaurin series, minus z raised to 4 by 4 plus etc. And here mod of z is less than 1. This is the condition. If mod of z is less than 1, then only means here this mod of z should be less than 1, then only you can expand it like this. And some more power series, you know this one, 1 minus z raised to minus 1 is 1 plus z square plus z cube plus etc. Means both are negative, then all will be positive here. Okay, and here 1 plus z raised to minus 1 will be alternate plus or minus 1 minus z plus z square minus z cube plus etc. Then 1 plus z raised to minus 2 will be 1 minus 2z plus 3z square minus 4z cube plus etc. And 1 minus z raised to minus 2 will be here 1 is plus and 1 is minus, so alternate plus or minus, here both negative means all are positive, 1 plus 2z plus 3z square plus 4z cube plus etc. And in all these the condition is mod of z must be less than 1. Okay, here if this one means if this term 1 minus say whatever x, this should be always less than 1, then only you can solve or you can use this formula no, this power series. Okay.